as you will see, today's lecture is brought to you by the Raspberry Pi 3 that is sitting in my office, which is as slow as, like, you know, the kids in preschool running across the schoolyard. That's about how fast that Raspberry Pi is. But the nice thing about the Raspberry Pi is it is such a nice, clean 32-bit machine that it's just nice. Today's lecture goes a lot better on the Pi. And it is nice that I can SSH into it from here in my office, so that's good. So basically, we are running on a Pi today. And today's lecture is about memory. So we're shifting segments, which is intentional, right? We just finished assembly code. Now you can go put that in the freezer, and you won't ever have to look at it again. And now we're going to move into memory with the idea, so I'll teach you about memory today, teach you about malloc on Thursday. That might spill into next Tuesday, and then you get to write malloc, which is a lot of fun. Then we'll shift into processes, and then you get to have even more fun. Okay, so with memory, one of the unfortunate parts about memory is that the constructs to mess with memory are dangerous. And so they're usually not, you know, they're not overly advertised because they are kind of dangerous. And so they're also not overly standardized. So a lot of the stuff I'll talk about it's not total POSIX standard. So if you're trying to run this stuff on your own machines, you know, your mileage may vary in terms of what's going to work and what's not going to work. Okay. And again, I'm doing this on a Pi largely because I like 32-bit pointers, so I'm not dealing with giant pointers. So that's why I'm doing this guy on a Pi. Okay, so memory, as I have said multiple times, is just a giant array. Okay, and then and the array, it goes from on a machine like the Pi, it goes from 0 to 8Fs, right? That's because that's 2 to the 32 minus 1. And whenever you have a pointer value, it's just like you're going to an index into that memory array. It's nothing sexy. It's just you got an array of bytes, your pointer is an index into that array of bytes. Now the problem is that array of bytes, not all of those bytes exist. And that's what a lot of today's lecture is on kind of what that looks like, what it means, and how to kind of mess with it with your programs. Okay? So the first thing we should do is we can prove that not all bytes exist, right? Because we can intentionally segfault if we want, right? So here, int main, let's do a segfault, char star s equals 0. That's not the segfault, right? That's fine. That's just putting 0 into some bytes. But now if I say, here, char c, and I say c equals star s, that's the segfault. Okay, so, uh-oh. I have no idea what directory I'm. Oh, I'm on my Pi. It doesn't matter. Okay, segfault. Now, what's going on there? And I'm going to go over this multiple times. What's going on on our machine is right here. I am issuing to the hardware. Actually, we've done assembly code. Right? So what's going on? I'm taking S. I said you could forget assembly code. I'm taking S, which is going to be at FP minus 4. I'm going to load it into a register, and then I'm going to take whatever's in that register, and I'm going to load that into another register. And so at that point, that load is saying load address 0. Okay? The hardware is what says, let me find address 0. Oh, it doesn't exist. Segfault. Hardware takes that exception, throws it to the operating system, says, hey, segfault. Operating system now reads that and says, okay, I'm going to throw it to the program segfault. Okay, and we're going to see later how to catch that. But those are the mechanics of what happens with a segfault. Okay, when you load your program, okay, so when you load your program, memory is partitioned, divided, I'll call it divided, into several regions, including, now I'm going to give the Unix name for this and then my name for it. Okay, so Unix calls it the text, which I think is a stupid word because it makes no sense to me whatsoever. I call it the code. This is where these are your instructions. All right, so when we were looking at assembly code, this is where all those instructions are going to be sitting. Okay, that's called the text segment. Why? I don't know. Okay, but that's what it is. Now, there's another segment. This is the next segment of code that exists is what I call the globals, because that makes sense. These are your global variables. When your program is compiled, the compiler can tell you exactly how many bytes worth of global variables you have. Okay? It's not a secret. It's not something you determine at runtime. You get that at compile time. And so when you load your program, the globals actually sit there in a memory segment that's loaded in for you. There's two Unix names for this. Okay? One is the data, and this are the initialized variables. Okay, so these are the ones that at compile time you know what their value is. So that gets set by the compiler so that when you load it into memory, those values are now already there for you. Okay. And then the other name, the second one, is called BSS. Why? I don't know, because someone decided to call it that. Okay? And that's our uninitialized data. So if you just say NI, that's going to allocate, that memory is going to be in the BSS segment. Okay? Now, fortunately, after this, the heap and I, or so Unix and I start to agree. So Unix and I, heap, right? So this is what you get with malloc and new in C++. Okay? This is its own memory segment, and this grows. Okay? So this grows. How? You'll see. But it's managed by the OS. Okay? And then Unix and I also agree on the stack. Now we've seen the stack, right? The stack's just a region of memory that you access via the stack pointer and the frame pointer. And even though it looks like it grows and it shrinks, it doesn't. It's actually a fixed size region of memory. So this is fixed size. Just seems like it's not. Okay? There are more parts of your memory than this, but these are the important parts. Right, and in the lecture notes, I'll draw the picture in ASCII. So if we look at the lecture notes for this lecture, right, this is what memory looks like. Right, typically you start at address 0, and then everything that I call a void means segfault land. Right, these are addresses that will segfault. Okay? So typically, in the beginning, you get a segfault. Why? Because a common mistake is for you to not initialize something, and if that gets initialized to 0, if it's a pointer, and it's initialized to 0, you'd really like to have that be a segfault. Okay? That's there to help you. And then typically, there's some memory allocated for the code. There may or may not be a void in here. In the old machines there weren't, but then on ours, on the Pi, there will be. Then you got the global variables. And this will be split into data and BSS. Okay? We'll have another void. Then we'll have the heap, right? And then this gets bigger and it grows down. So we have another void here, which gets smaller as your heap grows. And then you have the stack, which is some fixed size thing, which sits there. And then typically there's another void down there. So this is what your memory ends up looking like. Okay. Paging. Please remember this. Because why? Because I might test you on it. And when I test you on it, I would really like to see you get the answers correct. So, and I know from experience that sometimes you don't. Okay? Paging is a super important concept. So, all memory on your computer is partitioned into fixed size pages. Typically 1K to 4K. That's the range that your page is. Always a power of 2. Okay. Why? Because if I give you an address now, you can calculate the page just by doing a bit shift, right? If it's 1K and you give me an address, you can just do a bit shift to 10 bits, and that tells me the page number. Okay. Now with paging, there are a couple things, and this will be you'll get inundated with page crap when you take your operating systems course, because it's a big thing with operating systems. For this class, I don't teach you those mechanics because they're difficult, but the key is that whenever I issue an address, the hardware takes that page number, okay, performs error checking on it, right? So this is where the seg fault comes from. Hardware's going to take your address, turn it into a page number, look up in a table perhaps in some data structure, the hardware will look at and say, is this page legal for how it is being used? So if I'm loading it, I got to be able to read it. If I'm storing it, I have to be able to write it. If it's an instruction, I have to, where the program counter might point to it, it has to be executable. Those are all 3 protection modes that are maintained by the operating system for every page on a page-by-page basis. Okay? Very important. This is how the seg faults happen. Because when I issue an address, when I issue address 0, the hardware is going to look into a table and say, is this a legal page? And if it isn't, I get a seg fault. Now, if it is, now here's the magic that I don't teach you in this class. This is the magic you learn in the operating systems class, is that there is a translation table in, it's actually combination hardware memory, where the hardware will now take that address and say, okay, you wanted page 3? Well, guess what? That's page 532 really on the machine. I'm going to go there, right? So that it looks to me like I have this beautiful address space laid out from 0 to a bunch of Fs. Okay? But in reality, these pages are spattered all across memory. And that's set up by the operating system, and then the hardware makes it work. Now, caches add a whole other level of complexity to this, okay? Which I'm not going to go into. But the paging is important, and especially it's important to know that the protection boundaries go on the pages. Okay? There is a system call called get page size. So here, before I have my seg fault, if I want to see what the page size is, I can say printfd get page size. I'm sure it's going to give me a compiler warning. How many iterations do you think it's going to take for me to be able to compile this? Now I think it's going to be 2. Unistud. Oh, I could have. There we go. Whoop. Okay, 4K. Differs from machine to machine, but again, usually it's between 1 and 4K. Okay, now we're going to look at a program. Oh, and I should get rid of all the comments. Oh. Sorry. Repos. COSC360 Lecture notes? Shit. You're like, why don't you just work on the repo, Dr. Plank? Well, it's because I'm going to destroy it. So it's better for me to just copy it here. There we go. Oh, and it's a pie. Did you see how slow that was? Do what now? Yes. Yeah, 100%. When I teach, yeah, because I'm going to corrupt it, and then I just delete it because I don't want to corrupt my repo. You know, especially when I have like an odd thought that I just want to start doing. This way, it's cleaner. All right, so CS3. Oh, no wonder it took forever. I copied all the lecture notes. CS3. There we go. All right. Well, there they all are. Okay, that wasn't slow. That was pretty fast for the pi. Okay, let me take a look at this program. All right. This is a fun lecture. Look at the names of these programs. Break the heap, break the stack, look at memory, mess with memory, and segfault. It's like, that's a good day. Okay. Oh, I don't like any of these comments. Get rid of the comments. You don't need them. Okay, there we go. Okay. This is not POSIX standard. I wish it were. They change it all the time. It's weird. You have these three externs. What they are is, this is the address after the last byte of the text segment. So that's your last instruction. All right. This is the byte after the last byte of your data segment, which is your initialized global variables. And then this is the end of the BSS segment. Okay. And you can take they don't have types, but you can take the addresses of them. And that's how you know what these things are. So if we take a look at it, yeah. So what my program does here now, so we got a couple things. So here, let's walk through it. I've got 4 global variables, A, B, X, and Y, right? And even though I declare them A, X, B, Y, right, 2 of them are initialized and 2 of them are not. So I'm going to expect that A and B are going to reside in the data segment, and X and Y are going to reside in the BSS segment. Then I have this procedure that doesn't do anything. But I'm assuming that if I treat this procedure as a pointer, which you can, that's going to point to the text segment. Okay. Got myself a local variable. Where's that going to be? That'll be on the stack. Okay. Buff will also be on the stack. And then I say buff equals malloc 200. That's going to be on the heap. Okay. Then I print a bunch of stuff out. So I print out the page size. And then I print out what etext, edata, and end are. Again, end of the text segment, end of the data segment, end of the BSS. Why don't they call it EBSS? No one asked me. I wouldn't have called it BSS to begin with. Then I go ahead and I print out the code addresses. So you can treat a procedure like a pointer. That's what's going on here. So main and proc A are actually pointers. So these should be pointers into the text segment. Then I go ahead and print out A, B, and X, Y. I print out their addresses. Again, data, BSS, BSS. I print out buff, not the pointer to buff, but buff itself. That should be a heap address. And then these guys should be stack addresses. Okay. Then I call get pin. That gets my process ID. So this is a Linux thing. This isn't universal in the world, but it is on your Linux machines, and on, I guess the Pi is a Linux machine anyway. Is that if you look in /proc for each process ID of a process that's running, there is a file in there called maps. So what I'm going to do is I'm going to print that file. And what that file does is it identifies every byte of memory for me, which is a nice thing. So I go ahead and I say cat that, put that into buff, and then I call system on it, right? That's going to execute that. Should I have called snprintf? Yeah. I'm not going to, though, because this is a temporary directory, so it's not going to fix my lecture notes. Why do we care about snprintf? Yep, yep. Is it foolproof? No, because I can lie, right? Here, SNPrintf, buff 0x7, 1, 2, 3, 4, 5, 6, 7. There we go. In fact, when I first found, this is me being petulant. When I first encountered a system that gave me compiler warnings on sprintf, has anyone had a system like that? Yeah. So, you got a compiler warning on sprintf, and it says you have to use SNPrintf. I pound to find sprintf to do this, which, petulant. All right. Who knows how big the buffer is? Who cares? It'll still work. Okay. Yeah. Get a bunch of warnings on eText. Man, eText, I don't even know what it is. Yeah, you see, look at that. It tells me to do it. Whatever. All right, let's go ahead and run this. Oh, do I do anything after it? No, I just print out stuff. Okay. So bin, good memory. All right, let's go up to the top. All right, page size 4K, good. eText, that's the last instruction. You'll notice, is it on a page boundary? No. Page size is 4K. What's that? That's 12 zeros in binary. So I would expect 000 if it were to be a line, or if it were at the end of a page, it would be FFF. Okay, and it's not. Right? And then here's eData, and there's the end of the BSS. So how big is the BSS? Well, it's not very big, right? It's 12 bytes. So does that mean it's separated on a page boundary? No, it's not. In fact, these are on the same page. Okay? But it's on a different page, you'll note, right? That's on a different page than the text segment. Now if I look at the code, here's the code. Here are my code things. Do they look like they're in the text segment? Yeah, right? They're just below that. Here are my global variables. You'll note A and B are just below eData, and then X and Y are above eData but below N. So initialized, uninitialized. Right? It's nice, it makes sense. Got my heap address, okay, whatever that means. And then here are my stack addresses, which are big. Right? So they're all residing in different segments. Now here's the fun part. If you look at that proc map, okay, proc map has some junk in it, but it also has some useful stuff in it. So, first off, here's my text segment. Now you'll notice this one is aligned on page boundaries. You see it because you got 000 at the end. So what this is saying is from address 10,000 in hex to 11,000 in hex, that's my text segment. Those are my executable instructions. It's pretty small, isn't it? Right? 4K. It's residing on 4K. And in fact, if I look at the eText variable, it should be in between those two. Right? There's eText at 107E4, right? And it's right sitting there. Plus, what else do we notice? We've got protection here. This is hardware protection of the page. Executable bits set. Because your code's executable. If it weren't, you wouldn't be able to execute the instructions. Okay? You'll also note it's not writable. Okay? Code's not writable. Once you compile it, it gets loaded in and it doesn't get written. I don't know if that feels constricting to you, but man, life would be pretty bad if it were writable. I mean, it would just be virus city. That's one way to try to protect viruses. Okay. Now, we have this. I have to figure out what this segment is, because it doesn't correspond to any addresses. And what do you notice? It's read-only. So if I'm gonna guess that if I compiled a static string into my program, I bet that's where it would be. You want to test that? I like that I got the yeses. I got the yeses and I got blank stares. So here, let's do this guy. Here, char star here, let's print out, where we printed out buff, let's print out S. There we go. Will this work? And then we'll print out S. I'm hoping S resides in that segment. Sorry. Okay. Shit. Is S in the segment? Uh-uh. The segment starts at 20,000 and S is, where is S? It's in the code segment. Isn't that weird? It's been that way forever. What does that mean? If I try to change like that J in Jim Planck to a K, it's going to segfault because it's not writable. Let's prove it. So here, S0 equals K. That should give me a segfault. Yep. And that's because that address is sitting there in the code segment, and the code segment is not writable. Okay. All right, so now we've got, all right, so we've been through, there's the code segment, here's the, we don't know what this is segment, here's our global variables, right, and you'll notice, right, both A, B, and X and Y are sitting there in that region, okay? This one says here's my heap, right, starting at 9E, and you'll note my heap address starts at 9E, yay, and it's writable, right, these guys are both writable, so that's nice. They're not executable. Okay, then we get some junk here, especially like this one, right? Total null access. What do you think is going on there? Can't be anything good. Do we have any idea what these are? What's it?
The void from runner?
I'm sorry?
Is it the void from runner?
Well, the void, no, it's not. This isn't the void. So actually, everything in between here, that's a good question. Everything in between here is the void. So 0 to 1, void. 1,100 to 20,000, void. That's all segfault land. These are all the legal ones. Mr. Squires is skipping class again today, otherwise I bet he would know the answer. We'll test him next time we see him, if he ever comes to class again. It's a shared library. Okay. And on Windows, this would be a DLL. Right, if you've ever seen DLLs in Windows. What does it mean? So what's going on here is that libc.a, which has all of the stuff, standard stuff from C, so printf, sprintf, right, all that, fopen, all that stuff is compiled code. Well, since every program in the world uses them, we could compile, those instructions could all be in my executable, but in order to keep the executable small, what the operating system does is it compiles them into this SO file, loads it into memory, and then the operating system does magic to assign these addresses to be where that code is, and that code's shared among every process. Okay? There's some weird things about that because you got to think about like relative pointers and how that works, but that's not my purview. But that's what these .so files are. Those are shared libraries. They're like DLLs in Windows. Okay, I don't know what that is. Do we have a stack someplace? Oh, here we go. We got a stack. Right, and you'll note the stack has the addresses. There are stack addresses. They fit right here. So that's good. Well, that's interesting. In the lecture notes, the stack was actually executable, which seems like a travesty, right? That just seems like virus waiting to happen. Here, the stack's not executable, so that's nice. This one is. I don't know what these guys are. Okay, but anyway, it lets you read memory. Now, in the lecture notes, what I have is a clear indication that I had yard work to do because I drew that picture which in the lecture notes matches up with the output that I give you of this. So basically, and one of the things I'm trying to convey with this is most of your address space is the void, right? Most of your address space is getting a segfault. Okay? But here are your little regions that correspond to various things. You got your code globals heaps, and you got a bunch of junk. And then you get your stack way over here. Okay? All right. Now, let's have more fun. Any questions about this? I'm actually assuming this is new to you and not old to you.
What's a page boundary?
Okay, so a page boundary, again, so your computer allocates memory on these in pages, discrete units of pages. And what that means is that if I am accessing or if I'm reading or writing a byte, I need to have the whole page in memory. The whole page is going to be sitting there. And it's going to be and the protection of those pages, which is up here, is managed by the operating system, but enforced by the hardware. So a page boundary is going to be, for example, if I move from address 20FFF to 21000, I'm crossing a page boundary, because 20FFF is the last byte on that page, and then this is going to be the first byte on the next page. Okay. So what this is saying is this is the first byte of the next page. This is going to be a segfault. If I go to this one, it's going to be a segfault. Let's do it. Okay. My next program, this program, so if anyone has ever told you that C is an unsafe language, have you heard that before? C is an unsafe language? This is the very embodiment of that statement, right? Which is partially why we love C. Okay, mess with memory. Now what mess with memory does is it does the exact same thing as the other program, so it prints out all that stuff. Now, proc A, I've just added a printf statement to it. So if I call proc A, it's going to say hi. Okay. Prints out all the same junk as before. Okay. It does set. Okay, A is set to 4, B is set to 6. I think I set I to something, don't I? Yeah, I set I equal to some hex, 0xABCD. So those 4 bytes equal what? The 4 bytes of I are going to be CD, AB, 0, 0. Little endian. Okay, and then I say, hey, give me a pointer. This is something you don't normally do in your programs. Hey, enter a pointer on standard input. Okay. Then what it does, and you're going to do a character, either an R, a W, or an X. Okay. So I read it. How do I read it? I do an fgetS to grab the line of text, and then I do an scanf that reads in that value, right, into this variable pointer. Right? And what is pointer? I think it's a char star. Yeah, it's a char star. So I'm setting a char star. I'm setting the pointer's value from standard in. Again, this is unsafe. You don't want to do this. Okay? And then I also grab this character. And then on what the character is, I do things. So if the character is an R, then what I do is I read the value of the pointer right here into a character and print it out. Okay? If I say write, then actually set that byte to 0x67. Okay? And then if it's X, I memcopy it. I memcopy it into this procedure, and then I run it. So I'm actually taking a instruction location and running it with a JSR call. Right? This is great. Don't ever do this. But it's a good thing to learn about what's going on. Okay? So, let's run it. Oh, first off, look at memory grep buff. You might think this is either good or bad. You'll note when I run this program multiple times, buff gets a different address every time, what I call malloc. This is intentional, and it's even on different places on the stack. You see how that is? The stack actually has different addresses each time. This is for security, right? So that you can't load your so one source of malware assumes that when your process dies and then you load a new one, the operating system just grabs the pages that it used before. So now you have all the old programs pages loaded in, and if they're loaded in the same place, you can start just looking at them, right? If those were passwords, right? That's a big source of bugs, a big source of so one of the ways they combat that is by giving you different addresses each time, and also trying to, they don't scramble the pages, right? It's too expensive for the operating system to just wipe all the pages clean, so it doesn't do that. Maybe it should. Well, that's why this is going on. Okay, now we've got mess with memory. So, all right. Where are we? Here we go. There's A, right? If I read this, I expect to see 4. So if I put this address in here, and I read, good. I get 4. If I go 1 byte more, 0, 5, 9, what am I expecting? I'm sorry? Almost. Almost. What is A? It was an int, right? So the lowest byte of A is a 4. What's the next one? It's a 0. Right? It's going to be 4000 because it's a 4-byte integer. So that should be a 0. Right? If I do 60, that should be a 0. Ugh. Whatever. Ugh. 21060. That should be a 0. No. 0x21060 and a read gives me an 18. Was that not a? Oh, hex. Let's do that again. Where's A? 25. So, yeah, it should be 5A, not 60, 5A. I got the hex wrong. So 2105A, 0x2105A. Read, that should be a 0. Okay, good. All right. Now, there's the end of my BSS segment. It's not on a page boundary, right? Because if it were on a page boundary, it would be 21FFF. So all of the addresses from 21074 to 21FFF exist. I can read them, I can write them. My program doesn't make use of them. Okay? But since we have paging, I can read and write them. So if I say 0x21FFF, read, okay, I get a 0. It's fine, it's a 0, but I didn't get a seg fault. If I say 22000 and go on to the next page, now I get a seg fault. Okay? That's paging. Right? So it's important to know. That's what's paging. And why does paging exist? Well, there's a trade-off, right? Because most of the time when we use memory, it's grouped into big regions. And so I'm not wasting too much by partitioning that into pages. But it allows me to do my hardware protection on regions rather than bytes. If I did it on bytes, then my page table in the hardware would be huge. So since I have them be as I have pages be of some discrete size, my page table size is smaller, my hardware is smaller, and yeah, I waste a little memory, right? Because here I am wasting bytes, bytes 210FF to 21FFF. They're just unused, but since they're on the page, I can access them. Okay, let's go ahead and read on the stack. Here's I. Remember, I equaled 0xABCD. So if I take this address and do read, okay, get it right. What's this going to print out? print out CD because it's little endian. Yep. And if I print 1 byte more, that's going to print out AB. And if I do 1 byte more, it's going to print out 0. Okay. Now, I can write just as easily as I could read. So this, if I do this and say write, it's going to write the byte 67, 0x67 to that address. Okay? So, if I do this, my code's kind enough to print out I after that in A. And you'll note, I just changed I from ABCD to AB67. Okay? And if I add 2 to that address, 7E C59A16. Now when I print out I, it's going to print out 67AB67. Yep. And if I do one less, 0x, there's one more, sorry, 7EC59A17. Now it's going to be 6767AB67. Now, here's something fun. Oh, well, let's also go page boundary, right? So now, if I try, let's take a code address. So, a code address is, for example, here. Here's main, right? 10718. I can read that just fine. I don't know what's there. Right? Okay, the byte's 10. I have no idea, right? So it's a machine instruction. If I try to write it, segfault. Why? Code section's protected by the hardware. Okay? If, where are we? Okay, 10. So the code segment goes there. If I go to this address here and I try to read it, I should get a segfault because that's the first byte on the next page. So 0x11000, read it. I get a segfault. If I go 1 byte less, 0x10FFF, read, I get something. Again, page boundaries. I'm beating this into your head just because I've seen how many times you get this wrong on an exam. So, okay, here's something else fun. Here's buff. Right, this isn't the address of buff, this is buff. Okay, let's parse through what happens when I write 67 to this address. 67, in case you haven't memorized it, in hex, 67 is the ASCII character code of the lowercase letter g. I don't have that memorized, I just have it in the lecture notes. So if I write to this address, oh, I didn't write. Remember, buff was what I just read in here. That was the line of text I just read here. So buff is still that line of text, and now I changed its first character from a 0 to a G. So that's why it's that and that. It's confusing, but when you work through it, it all makes sense. Okay, now let's have a lot of fun. Let's execute something. Okay, so the address of proc A, which I have that prints out high, is that. So if I go ahead and do this and type execute, and what did that do? That, in my code, it took this address in 4 bytes and shoved it into that proc A variable, and then it called proc A. When I do that, it calls high. Can I do it to main? Why not? Where's main? Here's main. Right? So, yeah, it worked, right? New page size, new everything, and if we were gambling people, which of course we are not, if I scroll up and I look for the previous address of I, is it going to be greater than or less than this value? equal to, wrong, that's Will, I can crack on him. Wrong, moron. No, I'm kidding. Still kidding. Okay, this value should be less than the other one. Why? Well, because the other one was executing on a stack frame. When I made that call, it did a JSR to that address, happened to be main, whoop, frame pointer, stack pointer. So I was down here before, and it's up here now. So this value should be less than the value when I scroll. So here, let's store it. There. All right, if I were a gambling man, I would gamble that whatever value I see is going to be greater than that. Which kid should I bet on this one? I can bet my favorite grandkid. It's going to be right. Oh, wrong scroll. Oh, this is exciting. There it is. All right, let's compare them. Yay, grandkid lives. All right, because 3A is bigger than 3.9. Okay. If I want to break the stack, how do I break the stack? If I want to write a program that overruns my stack, okay? Overruns it so that I get a seg fault because I've gone over my stack. How do I do it? Yeah, infinite recursion. All right, that's certainly one way. So here, break the stack. Break the stack. All right, it does infinite. I call main. Right, I just call main with a different argc and I accelerate it. Right, I'm allocating 8K worth of memory on each one. I'm accelerating breaking my stack because it's allocating 8K. Okay, so. All right, now, we're gambling people. I want you, given what I've told you in this class, and of course you remember every word I say, I want you to tell me what's argc going to be roughly when I break the stack, when I get the seg fault. Do you remember how big the stack segment is? Close. 8 meg. It's 8 meg. So if it's 8 meg, this should be right at 1,000. Right? Because 8K. So let's run it. Yep. It's not exactly, but it's pretty close. Okay. How else could we break the stack? I don't know if this one actually works or not. But here's another way we could try to break the stack. Right? Char T. 8. So here, let's make it something bigger than that. There you go. There we go. All right, that's 9 megs. Now what's going to happen? When I call this, it's going to say push giant number to get the stack pointer way up here. Is that necessarily going to cause a seg fault? It's only if I access something it's going to seg fault. So I don't know if this one's going to seg fault or not. Well, here, let's get that out of here. Let's just start with that. Oh, you whiny ass compiler. Okay, no seg fault. Now, I will contend the seg fault will happen. Here, let's make this a global variable so we know it's not on the stack. And let's say I say C equals T0. Right? That should give me a seg fault. Right? Because now it's going to try to get at whatever the stack pointer is pointing to, and that should be above the stack segment. Oh, good day. Now, let's try. If we're having a great day, let's access the very last element in here, and that shouldn't be a seg fault. All right, so here, 8, 1, 2, 3, 4, 5, 6. Right, that should be legal. Oh, look at that. All right, so should we figure out where the seg fault happens? That's going to be hard. Why is it going to be hard? Because I can't call printf. If I call printf, it's going to allocate a new stack frame, which is going to be off the stack. So is there anything I can do? I can't even call system.
Yeah, right.
Still doing it. Still going to use the stack. Everything's going to use the stack. So how do I do it? I don't know. I'd have to write a signal handler. I'm not going to. It's too much work. All right, that was fun. All right, let's break the heap. How do we break the heap? Well, we just call malloc something that's too big. Or maybe we just call malloc a bunch of times. So here, if we take a look at break the heap. All right, what am I doing? So that's a big ass loop, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I'm doing this for 10 to the 9th iterations. I'm allocating a megabyte for 10 to the 9th. Right? Now I can guarantee you my Raspberry Pi does not have that much memory. All right, so we should break the heap here. Yay, we broke the heap. Right? Oh, 2 gig. Okay. Right. It's roughly 2 gig is where we broke the heap. That's about what my Mac or what I don't know. Does my Pi have 2 gig of memory on it? I guess that's right. Pi 5s, you can get them with 4 or 8. Now, operating systems will set up memory so that you get to access more memory than you actually own. Again, this is in your operating systems course. It's called demand paging. And what it does, what happens is that when you start using more memory than you actually have, what the OS does is it says, hey, you haven't used this page for a while, I'm just going to flush it to disk. And now I'm going to set it null access, and when you try to access it, I'll pull it back from disk. It's called demand paging. Super expensive. But have you ever, for example, on my Mac, how many of you all have ever done this? Probably haven't. You write a program, it's got a memory leak in it, a big old memory leak in it. Okay? So it's running, and it's consuming all of memory. And then what happens? Like the next time you touch Chrome, it takes forever to load. And the next time you touch Photoshop, it takes forever to load. That happens in general with Photoshop. You don't use Photoshop. Okay? But if you leave Photoshop up for a long time, all of its memory gets thrown to disk, so that by the time you use it again, it takes forever because it's got to pull all that stuff back from disk. Okay? So for example, in this one, I'm pretty sure on my Mac. Do I want to kill my Mac like this? No, let's kill like a Hydra machine. That's more okay. Okay. First off, should we find out who's on it and apologize to them ahead of time? Nah. How much do they pay for that machine? Let's see who's on there. Oh, no one, just me. Oh, I bet they're... Wow, unused. That's sad. I wanted to hurt someone. Okay. I'm joking. Put in my reviews. He hurts people. Okay. Sure. Break the heap. Huh. I can guarantee you that's more memory than's on that machine. Right? So it's swapping some shit to disk. Everything's to disk now. Uh-oh. Now it's getting slow because it's swapping my own stuff to disk. Oh, then it killed me. Malik didn't even return null? Oh, did you see that? What I said? They probably not. It is. Oh, no, it isn't. I was going to say, I probably couldn't have even read that. Break. That's interesting. Why do I care? Okay, let's back up. What's happening is that Malik's not returning null, my process is getting killed. Okay, so what happened? Meant that when I did this Malik call, my operating system killed my process. So why does this piss me off? Because we have semantics, right? I have a correctly written program that should fail gracefully when I run out of memory. And now, whoever the jackass is who wrote that operating system has denied that of me, and now I have more non-portable code. I want you all to feel this someday. Like someday, it doesn't matter, in 3 or 4 years, you're going to see something like that and you're going to have an emotional response to it, and then you'll I don't know if you'll thank me or blame me, but I hope you do one of them. I hope you have the emotional response. It's actually hilarious. My wife, Will, noticed this in class. The kid gave a talk, and then he said he used Python to generate the results, and I didn't see my wife was behind me. She snorted, right, didn't she? She snorted. She knew it. She's like, Python, oh my God. That's awesome. Awesome. She has no idea what a computer is. I shouldn't say, well, no, I could. But she could have explained that erasure coding thing. That's one thing I'll give her. Okay. Let's click. Oh, you're going to love this one. I don't know if 12 minutes is enough. You happy to hear that? What am I doing? Here, let's enable. There we go. 675-253. Whoever's texting Mr. Squires, go ahead. Tell him that's what it is.